Hello there, welcome to Ethio-Hahu tutorial. I'm Getachew and today we are going to see about mechanical waves. Before we proceed to what mechanical waves means, let's say something about waves. Wave is any disturbance that can propagate from one point in space to the other point in space while carrying energy and momentum. Wave can propagate either through material medium or vacuum from one point in space to the other point in space. For a wave to be produced, there must be a source of wave. That source of wave, when oscillates or vibrates, it generates wave. And such a wave can propagate from one point to the other point. And this wave can be either mechanical wave or electromagnetic wave, depending upon the medium through which they propagate. Mechanical waves are waves that can propagate through material medium, and electromagnetic waves are waves that can propagate through vacuum as well as through material medium. Therefore, waves can be classified as mechanical and electromagnetic. Mechanical waves are waves that can necessarily require material medium to propagate through. Examples of mechanical waves are water wave, wave in a string, and sound waves. These are mechanical waves. They need material medium to propagate through. On the other hand, electromagnetic waves are waves that can propagate through both vacuum as well as material medium. Electromagnetic waves do not necessarily require material medium to propagate through. For example, light. Light can propagate through vacuum as well as through material medium. And in this class, we are going to see only mechanical waves. Let's throw a stone into a pool or a lake, like this. Here is the point of impact, and from the point of impact, the spherical wavefronts will spread out, and such waves are said to be mechanical waves. Pulse versus periodic waves. What is pulse and what is periodic waves? Here we have a string, and if we give one initial disturbance to this string, we can have one pulse. This is wave pulse. This wave pulse propagates through this medium as a result of this one initial disturbance. But if the disturbance is continuous, the source generates continuous or repeated waves, and these repeated waves propagate through this string, and this is known as mechanical waves because these waves propagate through this material medium. Any wave that needs a medium such as water in which to travel is called mechanical wave. A single wave pulse can be formed by giving a slinky, a spring or rope a single up and down motion. If we continuously disturb the rope, each successive sections of the string will move up and down, moving the wave forward along the slinky, as we have seen so far. And such a wave is said to be mechanical wave. In continuous wave like the one that's shown above, a continuous vibration of the source causes the particles within the medium to oscillate about their average position in a regular, repetitive, periodic pattern. The source of a mechanical wave is this repeated motion or vibration, and the wave moves energy from the vibration through the medium. Wave can transport energy and momentum. Mechanical waves can be classified as transverse wave and longitudinal waves, depending upon the displacement of the particles of the medium and the propagation of the wave. For example, if we have a string, and if this string is disturbed, the particles of the string will move up and down. This is a string. The propagation of the wave is horizontal, whereas the displacement of the particles of the medium is perpendicular to the propagation of the wave. And such a wave is said to be transverse wave. And such a wave is known as transverse wave. A transverse wave is a wave in which the displacement of the particles of the medium is always perpendicular to the propagation of the wave. Whereas longitudinal wave is a wave in which the displacement of the particles of the medium is parallel to the propagation of the wave. For example, if we have a spring like this is the direction of the wave, and the particles of the medium also displace along the direction of the wave, and such a wave is said to be longitudinal waves. Longitudinal wave is different from that of transverse wave, in which in longitudinal wave the particles of the medium is parallel to the propagation of the wave, whereas in transverse wave the particles of the medium moves perpendicular to the direction of the propagation of the wave. When waves travel in water or through a rope, a spring or a string, the particles within the medium vibrates up and down in a direction perpendicular or transverse to the direction of motion of the wave energy, as shown below. The propagation of the wave is to the right, whereas the particles of the medium, such as water or a string or a spring or rope, is perpendicular to the propagation of the wave, and such a wave is said to be transverse wave. When the particles are displaced upwards from the average position, also called the resting position, they reach a maximum positive displacement at a point called crest. The maximum displacement of the particles of the medium from the equilibrium position is known as crest. Whereas particles below the average position fall to a maximum negative position at a point called trough. That is, this is the negative maximum displacement of the particles of the medium and is known as trough, whereas this is the maximum displacement of the particles of the medium, which is known as crest. And we have successive points of crest as well as successive points of troughs. This crest as well as troughs can determine the wavelengths. One wavelength is the distance between two consecutive crests or two consecutive troughs. The distance between this crest and this crest is known as one wavelength, or the distance between this trough and this trough is known as one wavelength. Therefore, one wavelength is the distance traveled by the wave from one crest to the next crest, or from one trough to the next trough. In a longitudinal mechanical waves, the vibration of the particles within the medium are in the same direction in which the wave is moving. If we move our hands back and forth like this, wave will move along this spring. And along this spring, we can have successive points of compression and points of rarefaction. And this determines the wavelengths. The distance between two consecutive rarefactions or two consecutive compressions is known as one wavelength. But in general, in this case, the direction of the propagation of the wave is to the right, whereas the direction of the displacement of the particles of the medium is also to the right. Since they are parallel to each other, this type of wave is known as longitudinal wave. A compression is an area where the coils of the slinky come together, and expansions are regions where the coils are spread apart. An area of expansion is called a rarefaction. The compressions and rarefactions in a longitudinal wave corresponds to the crest and troughs of a transverse wave. A wave can be characterized by its wave frequency, wavelength, and amplitude. The frequency of oscillation, the amplitude of oscillation, and the wavelength. If a string is set to vibrate about this equilibrium position, the particles of the medium moves up and down. This point is crest, and this point is trough. And this point is points of maxima, and this point is points of minima. The distance between two consecutive points of maxima is known as one wavelength. This points of maxima and this points of maxima. The distance between two consecutive crusts is known as one wavelength, or the distance between two consecutive troughs is known as one wavelength. The maximum displacement of the particles of the medium from the equilibrium position is known as amplitude, and the number of oscillations of the wave per unit time is known as frequency. Having seen this, the wave speed v is defined as the time rate of change of displacement. A wave advances a distance of one wavelength in a time interval equal to one period. The time required to move from this crust to this crust is known as one period. In this one period, the wave propagates one wavelength. And if the wave advances one wavelength, delta x is equal to lambda, in a time interval delta t is equal to one period, then the wave speed is equal to, in place of delta x, substitute lambda, and in place of delta t, substitute period. That is lambda divided by period. And this is equal to lambda times frequency, where frequency is equal to 1 over period. Having seen this, let's see exercise. This sinusoidal wave shown below is traveling in the positive x direction. This is the positive x direction, and has a frequency of 18 Hz. Find A, amplitude, B, wavelength, C, period of oscillation, D, speed of the wave. To solve this, the first one is amplitude. This is the maximum displacement. This is the equilibrium position. This is the maximum displacement, positive A. This is the minimum displacement, minus A. And this is the distance between points of maxima and points of minima. From this point to this point is amplitude. Therefore, from this point to this point is twice of the amplitude. And from peak to peak distance, this peak to peak distance is known as 8.26 centimeter. Therefore, A, this peak to peak distance, twice of amplitude, because from this point to this point is A, from this point to this point is also A. The distance from this point to this point is twice of A, is equal to 8.26 centimeter. Dividing both sides by 2, A amplitude is equal to 8.26 centimeter divided by 2, and amplitude is equal to 4.13 centimeter. B, the wavelength. Wavelength is the distance between two consecutive crust or trough. This is one wavelength because this is crust and this crust. The distance between these two consecutive crusts is known as one wavelength. Lambda. The distance between a crust and the nearby trough is known as half of the wavelength. This half of the wavelength is equal to 5.20 centimeter, because this is crust, this is trough. The distance between this crust and the next nearest trough is half of the wavelength, and this half wavelength is equal to 5.20 centimeter. And multiplying both sides by 2, lambda is equal to 2 times 5.20 centimeter, and this is equal to 10.4 centimeter. The wavelength is 10.4 centimeter. C, given that frequency is 18 Hz. What is period? Period is equal to 1 over frequency, because from the relationship between frequency and period, frequency is 1 over period, or period is equal to 1 over frequency. This is equal to 1 over frequency is 18 Hz, and this is equal to 0.0555 second, and this is equal to 55.5 millisecond. This is the period of oscillation of the wave. And d, the speed of the wave. D, the speed is equal to lambda over period or lambda times frequency. And v is equal to lambda, wavelength is 10.4 centimeter times frequency is 18 hertz. This is equal to 1.872 meter per second. V is equal to 1.872 meter per second, or is equal to 187.2 centimeter per second. The next exercise, a wave traveling in the positive x direction is shown below. Find the amplitude, wavelength, speed, and period of the wave if it has a frequency of 15 Hz. In the figure, delta x is equal to 72 centimeter and delta y is equal to 25 centimeter. We need to find the amplitude, wavelength, wave speed, and period. Given that frequency is equal to 15 Hz. To find the amplitude is the same as delta y from the equilibrium position. This is the maximum displacement of the particles of the medium. Therefore, A amplitude is equal to delta y, and delta y is equal to 25 centimeter. 25 centimeter. B, wavelength. Wavelength is the distance between two consecutive crust or troughs. Or we get this point after one period, and the distance traveled by the wave in one period is known as one wavelength. Therefore, the distance between this point and this point is known as one wavelength. Wavelength is equal to delta x, because we get this point after a time interval of one period, and the distance traveled by that one period is one wavelength, and delta x is 72 centimeter. C, wave speed. V is equal to lambda divided by period or lambda times frequency. Wavelength is 72 centimeter, 0.72 meter, because 72 centimeter is 0.72 meter. 25 centimeter is 0.25 meter. Times frequency is 15 Hertz, and this is equal to 10.8 meter per second. 0.72 meter times 15 Hertz is 10.8 meter per second, and this is the wave speed. D, the period of oscillation. Period of oscillation is equal to 1 over frequency, and this is equal to 1 over 15 Hertz, and this is equal to 0.0666 second. Therefore, period is equal to 66.7 millisecond, where milli is equal to 10 to the power of minus 3 prefix. This is the period of oscillation. The speed of a transverse wave in a string. For a vibrating string, there are two speeds to consider. One is the speed of the physical string that vibrates up and down, transfers to the string in the y direction. This is the direction of the wave. This is the direction of motion of the physical medium, the particles of the medium. And the direction of motion of the particles of the medium is always at right angle to that of the propagation of the wave. Therefore, the physical medium oscillates up and down while the wave propagates horizontally. Therefore, in this case, there are two motions. One is the motion of the physical medium, up and down motion, and the other, the speed of the wave. Therefore, if we pull the string up to a maximum point and release the string will move to the negative displacement minus a and back to that point. And the time required by the particles of the medium to move from this point, from the maximum point to the lowest point and back to the initial point, is 1 period. The time required by the physical medium to move from this point to the lowest point and back to its initial point is 1 period. And in this 1 period, the distance traveled by the wave is 1 wavelength. In this time interval, the propagation of the wave is 1 wavelength. The other is the wave speed, which is the rate at which the disturbance propagates along the length of the string in the x direction. The speed of a transverse wave in a string of tension T and linear density mu is equal to mass per unit length is given by this. V is equal to the square root of tension divided by linear mass density. For mu is equal to constant, linear density is equal to constant. If T is increased, V increases, and if tension decreases, the speed decreases. For constant linear mass density, if we increase the tension in the string, the speed will increase, and if T gets smaller and smaller, the wave speed gets smaller and smaller. For constant T, if linear mass density is decreased, if we decrease this for constant tension, the speed will increase. V increases, and if we increase the linear mass density, if this is increased, the wave speed gets smaller. Therefore, the relationship between wave speed, tension, and linear density is this one. The speed of a transverse wave in a string of tension T and linear density. Mass of the string divided by the length of the string is known as linear density or linear mass density. And this relation is used to calculate the speed of a transverse wave in a string. Having seen this, let's do exercise on a transverse wave. Here, tension is maintained in a string as shown below. The observed wave speed is v is equal to 24 meters per second when the suspended mass is 3 kg. A, what is the mass per unit length of the string? And B, what is the wave speed when the suspended mass is 2 kg? First, let's do for A. In this case, if M is equal to 3 kg, the gravitational force weight is equal to 3 kg times 10 meters per second square, which is equal to 30 Newton. And the tension in the string is upward. Since this string is inextensible string, the tension in the string remains the same. And this tension is equal to the weight of this object. Tension is equal to the weight of the object, because from Newton's second law of motion, net force is equal to mass times acceleration, but the acceleration is 0. The net force acting on this block is tension force minus weight of the object, which is equal to 0, and tension is equal to the weight of the object, which is equal to 30 Newton. Having this tension, given that V is equal to 24 meters per second, we have found tension is equal to 30 Newton, and we are asked to determine the linear density. Since V is equal to the square root of tension over linear density, squaring both sides, V square is equal to tension divided by linear density. And from this, linear density is equal to tension divided by V square. Tension is 30 Newton divided by V is 24 meter per second, the whole square. If we divide this, we get 0.052 kilogram per meter. This is the linear mass density of the string if the suspended mass is 3 kilogram. But if we change the mass of this suspended object, the tension in the string will also change. B. What is the wave speed when the suspended mass is 2 kilogram? When this is equal to 2 kilogram, again, net force is equal to mass times acceleration. This object is in equilibrium. Acceleration is 0. The net force acting on this block is tension force upward minus the weight of the object, which is equal to 0. The weight of the object is downward. Mass times gravity. Mass is 2 kilogram. Gravity is 10 meter per second square, which is equal to 20 Newton. And tension is equal to W, which is equal to 20 Newton. Then, the linear mass density is the same because the linear mass density is the property of the string. The linear mass density is equal to 0.052 kilogram per meter. And here, the tension in the string is changed to 20 Newton. Because of what? Because of this mass. And the tension gets smaller or decreased than the previous one. Therefore, the wave speed is equal to the square root of tension divided by linear mass density. This is equal to the square root of tension is 20 Newton divided by linear mass density is 0.052 kilogram per meter. And this is equal to the square root of 20 divided by 0.052 is equal to 19.6 meter per second. And the wave speed is decreased because when the 3 kilogram mass is suspended from this string, the tension in the string is 30 Newton and the wave speed is 24 meter per second. Whereas if the tension in the string is decreased to 20 Newton for the same string, then the wave speed gets smaller because the wave speed is proportional to the tension. If we increase the tension, the speed will increase, and if we decrease the tension, the speed will decrease for constant linear mass density or linear density. In this case, this linear density is the same for both cases. And this is all about today. Next, we'll see another topic. Until then, have a nice time.